again, it's easier if you have the headers and rows distinguished. So it should look something like this. 1, 2. There must be a reason why Newton does that. I don't know why. 1, 2, 3, 4. And so you could imagine that 1 and 1, this one here meet up at 1. 2 and 1 meet up at 2. So you can see how I'm copying the table over, right? You can just imagine a line going vertically here and a line going horizontally. Anyway, commutative and associative properties are the same as what you've learned before. Remember, the commutative property would be if you could take 1 square 2, and that should equal 2 square 1. The commutative property means you could reorder things and they make the same thing. Okay? So let's check that. If you go 1 in the rows, 2 in the columns, you get out 1. If you go to 2 going across the header row and go to 1 in the column, they match up at the number 2. So we just saw the commutative property is not obeyed here. If you switch up the order of operations, it's not true. So it's not commutative. Okay? Let's check associative. And you probably know where I'm going with this now that you've seen. The associative would be 1 squared 2 squared 3 is the same thing with a parentheses here as 1 square 2 square 3. Okay, so I got to do the parentheses first, right? And that's what the associative property is all about. If you do 1 square 2, you get out 1. And notice I just picked any 3 numbers. You need to really check this for all the numbers, okay? For all matchups of numbers. So, oh boy, volunteer, taxes. Okay, so 1 square 2 gives us 1. 2 square 3. 2 on the row, 3 on the column over here. It makes us line up with the number 1. And so 1 on the row, 3 on the column gives us 3. 1 in the row, 1 in the column gives us 1. So the order you do the operation in does matter. The associative property doesn't hold. So it's not commutative or associative because we found counterexamples. We found something that made the commutative property be false. We found something that made the associative property be false. So, yeah, it's tough. Okay, closure. I think this is the first time I've done this in a video. If a set is closed under some sort of operation, it means you should be able to take any 2 elements, do the operation, and you should be able to get another element in that set. So we have the set of integers 3 or larger. 3, 4, 5, ... means that you can do 6, you can do 7, 8, 9, 10. So the question is, can you multiply any of these numbers and get another number in the set? If you can, it's closed under multiplication. Like in other words, 3 times 4, that makes 12. And 12 will be a number up here, right? So far, we haven't found anything to disprove closure. 3 times 5 makes 15. 15 is going to be a number in these ... 3 times 6 is going to be 18. That's going to be a number. 4 times 5 is going to be 20. We're going to get to 20 eventually. So anytime you take any pair of numbers, multiply them, it becomes another number in the set. That means, yes, it is closed under multiplication. Have associative property. So we've already done this one. This is where it's a lot of checking. 12, alien operation 13, alien operation 14. That should equal, if you put parentheses around here, that should equal 12, alien operation 13. This is the associative property, right? Alien operation 14. And so if you do 13 operation 14, 13 in a row, down to 14 on the column, that gives you 12. 12 operate 13 gives you 12. And so 12 gives you 14 on the left. And now 12, 14 gives you 13. It is not the associative property. It doesn't hold. We found a counterexample. If it did work, though, you're going to want to go back and check other options. Okay? Keep working until you've thoroughly convinced yourself. There's ways later on in mathematics where we prove that something's closed under the associative and commutative property. Ways we show that something's commutative and associative, ways we can prove closure, but right now, since it's just a limited amount of examples, you just want to check every option. So given the identity element of 6, so this is the first time we've seen an identity element. Okay, an identity element means it doesn't care what you do with it. It always spits out the other operation. So they told us that 6 is the identity. Okay, so that means if you do 6 triangle 7, you should get 7. If you do 6 triangle 8, you should get 8. If you do 6 triangle 9, you should get 9. And if there's an element 10, 6 triangle 10 should give you 10. Because just like the identity property of addition, which is just adding by 0, okay? Whatever you do, when you apply the identity property, it gives that original, whatever element you give us, if we apply the identity operation, you get that same element, okay? The identity property of multiplication, give me any number. 5. If I use the identity property of multiplication, I spit back out 5. So if 6 is the identity element, I don't care what you do with the operation, what number you give me to operate with it. It's always going to spit out that number. Okay, so now we know 6 is the identity element, what the identity element means. We can learn what the inverse means. Okay, an inverse means it's another, let's see, with inverse of 9. So if two numbers are inverses of one another, you should be able to operate the two numbers together and get the identity. In other words, like some Plato numbers, like -2, its additive inverse, additive meaning adding, is 2, okay? -2's additive inverse is +2. Because if you do -2 plus 2, it gives you the identity element of 0. The identity element of addition is 0. And so, let's say the number 4. Its multiplicative inverse is 1/4. Because if you multiply them, you get the identity element of multiplication, 1. You get that thing that you can use to always spit back out whatever element you give it. Okay, I'm not really talking in mathematical terms. This subject's definitely not my forte, but yeah, I can definitely help you answer these questions. So please feel free to send a screenshot if you think I haven't covered one, and I'll definitely help you with it. But yeah, back to this idea of an inverse. An inverse element is something you can operate your element of 9 on, and it'll give you 6. Okay, so basically we're looking at 9. And we want to go down the 9 column and see what spits out 6. Oh, itself, okay? 9 spits out 9. 9 and 9, if you operate those together, that gives you the identity element of 6. That means 9 is the inverse, okay? So when you're looking for an inverse, you're looking for the other elemental pair that spits out the identity element. Let's see if we can find another example like that. Yeah, so here's another good one. The identity element of the operation table. So first, we need to know what the inverse is before we can find that, okay? So we're looking, let's start with J. If J is the, oh wait, no, I think I was getting my words confused. They just asked for the identity element. That means we're looking for the element where if you give it any other element, it just spits out that second element. So looking at J. J paired with J gives you M. It's not spitting out the other element. So we know J is not the identity element. K paired with J gives us J. K paired with K gives us K. K paired with L gives us L. K paired with M gives us M. So K is the identity element because it doesn't care what you pair it with. It's just going to spit out that second element. Just like 0 is the additive identity element. Because 0 doesn't care what you give it. If you give it the number 652, 652 plus 0 is still 652. It doesn't change it. Are we having fun? Given the mathematical system defined in the table below. Come here, B, alien operation. So this looks like the associative property, right? They've changed. The only thing the order is the same. The only thing that's changed is the grouping, the parentheses. So they told us they want us to compare. Okay. So let's actually do this out. B aliens. C, alien operation. D. Remember, this confused me so bad. Oh, so we're asked to compare them. This confused me so bad when I was in school. I was having a hard enough time in my statistics class, and I looked up on the board, and then they made a whole new symbol. Kind of looked like a plus symbol. Okay, so we're supposed to find out what this. So we're supposed to compare these. So let's do. You got to do parentheses first. So this means C on the row, D on the column. That spits out A. Okay, and then if we do B on the row, because we go left to right, B on the row, A on the column, that spits out B. Let's compare that to what we get over here. B on the row, C on the column gives us D. D on the row, D on the column gives us B. Okay. So because these two are equal to each other, so it's either these two, right? We just found out that these two operations are equal to each other. You want to choose this one because, like I said before, the system may be associative. It worked for these three elements, but it might not work if we throw in element A. So you're going to want to still check all the other operations. Okay, remember closed under multiplication. That means you can multiply any two elements in the set and get another element that's in the set. Okay, so like this one is not closed because 5 times itself, those are two elements that are in the set. 5 times 5 makes 25, or 5 times 4 makes 20. Those are not, 20 and 25 are not in the set, so that's not closed. Same here. 5 times 4 makes 20. 20 is not in the set, that's not closed. 0 times 1 is 0. That's in the set, so that's closed. 1 times 2 is 2. 2 is in the set. So it's looking closed. 2 times 3 makes 6. 6 is going to be a number. This one is closed under multiplication. Oh my God, when have we done this up? We've given them Okay, they're asking for an inverse. So that means we have to find an identity first, right? So 3 paired with 3 gives us 5. That's not the identity. An identity should spit out whatever you're pairing it with. 4 paired with 3 gives us 6. That's not the identity. 5 paired with 3 gives us 3. 5 paired with 4 gives us 4. 5 paired with 5 gives us 5. 5 paired with 6 gives us 6. So 5 is the identity because whatever you pair it with, it spits out that second element. Okay, so which elements have an inverse? If two elements have an inverse, if two elements are inverses of one another, I should say. If any two numbers are inverses, you should be able to perform the operation on them and get the identity element. You should be able to get 5. So 3 paired with 3 gives us 5. 4 paired with 4 gives us 5. So 5 paired with 5 gives us 5. Let me think about this here. They all have inverses. It's a tricky one. They all have inverses, and the inverse is itself, right? You're looking for pairs that would give you the identity. 3 has an inverse. It's 3. 4 has an inverse. It's 4 because 4 paired with 4 gives you 5. That threw me for a loop for a second. Okay, does it have the commutative property? We've checked this one. I think that's it for this topic. It's going to start checking them off. Let me know if there's something similar to these ones. I'm going to make another video, but let me know if there's something similar to these ones you want me to do.